Well, hello and welcome. This is the first lesson for this semester. Well, the first content lesson. And this chapter is about intermolecular forces and then the consequences thereof. So I'm sure you've heard of the internet before. The internet is the connection of computer networks. So between computer networks, so you have like Hawaii.edu and Facebook.com, for instance. So you can connect between those networks via the internet. And then we have our own intranet that is within our own network. So that's where uh, I can submit the grades, where you register for classes, the library portal, the email. This is all within the intranet. So maybe if you're on campus and the internet's down and you can still register for your classes, that just means that the internet is down. The intranet is working just fine. So internet tends not to go down anymore. So happened when I was younger, I guess. So let's talk about intermolecular forces and intramolecular forces. So intermolecular forces are between molecules. Intramolecular forces are within the molecules themselves. Generally speaking, intramolecular within the molecule, those forces are stronger than the forces between the molecules. So generally speaking, if you look at water, for instance, water here has, if you look at the hydrogen-oxygen bond length, is about 96 picometers. A picometer is 10 to the minus 12 meters. And then between two water molecules is 300 picometers. So the greater distance, generally speaking, means there's less bonding. And let me talk about the states of matter: solid, liquid, and gas. So to remind you, solid means defined shape and defined volume. Liquids do not have a set shape but have a set volume, and gases have neither set shape or set volume. And the reason for that is because solids have relatively strong intermolecular forces, so it keeps them together. So if you look at something like my Apple Pencil here, this is a solid. So, and what's keeping this thing a solid is that the forces between the atoms and or molecules, and generally speaking more molecules, and so there's some metal up here, that would be between atoms. Generally speaking, this bonding is stronger, relatively strong. Liquids, though, it's a kind of a medium strength, so they're moving around enough that they're free to move, but they still hang out together. And liquids have a set volume, so if you pipette 25 milliliters of hydrochloric acid into a beaker, you assume, oh, that's going to be 25 milliliters because the liquid is not going to change its volume. So we kind of instinctively know that we've been using water. Water is a very common liquid that we use, but the liquid does not change its volume between containers. Gases, on the other hand, just fill whatever container they're in. So these have relatively weak intermolecular forces. And also the change of phase. So let's pretend that my fingers are like water molecules, so these V's here. So if it's a solid, they're just kind of sticking together. Solids don't move that much, and temperature means average kinetic energy. So if these start moving faster, you can get to a point where water or ice will melt. And then the water molecules will kind of hang around together, and they'll heat up, and after enough energy, they fly apart, break their bonding. That's what a gas is. So that's boiling. When you melt something, you put enough temperature energy to break the intermolecular forces to go from solid to liquid, and when something boils, it has enough energy that it will go from liquid to gas phase. And solid and liquid are also known as condensed phase because there's a lot more matter in the condensed phase than the gas phase. So you can move your arms in the air. There's matter here. Air is a gas. Try moving your arms underwater, or along the beach with some sand. Try pushing sand out of the way with your arms, with your hands. It's harder. It's harder than air. Why? Well, because there's more material. There's just more matter, and so much more actually. So if you see condensed phase, that means solid and liquid. Okay, so why do things have intermolecular forces? It has to do with the bonding between them, obviously. And what's the bonding? It's electromagnetic, it's electrostatic, it's the Coulombic force. And here is the Coulombic force. The force is a constant 1 over 4 pi epsilon naught times Q1, Q2, charge of 1 times the charge of second over the distance squared. So how do you make this force stronger? Well, if you make the distance smaller, it'll get stronger. And if you make the charges bigger, it'll get stronger. So generally speaking, the weaker charges with ions, so of different molecules, ions with small charges that are big are going to have weak forces. In contrast, things that are highly charged, that are tiny, are going to have really strong forces. So we'll talk a little bit more about that later. But let's look at two water molecules here, and I've drawn them. You might notice there's this lowercase, that's a delta. So that's the Greek letter delta. And I've written the first four letters of the Greek alphabet there. The lowercase delta means partial. So there's a partial negative by the oxygen, a partial positive by the hydrogen in water. And what I mean by partial, it means less than 1.6 times 10 to the minus 19 coulombs. That's the charge of a proton, or negative charge of an electron, for instance. And then 3 dots there to show the attraction. So let me talk about the intermolecular forces. I'll start with the weakest one, and the weakest one is known as the London dispersion force. Sometimes it's referred to as the London force, sometimes called the dispersion force, sometimes called the London dispersion force. They all mean the same thing. And let's look at two xenon atoms. Xenon is a noble gas. It tends not to bond with anything. It can bond covalently, but it tends not to. It's happy with all of its 8 valence electrons. But say two xenon atoms approach each other, what happens? Well, the electron cloud of one will interact with the electron cloud of the other, and it can distort the electron cloud, or the electron cloud will be attracted to the nucleus of the other one. So either way, the atom will polarize, meaning it will distort, the electron cloud will distort, and then will create a partial positive and partial negative. And what I mean by partial, I mean less than 1.6 times 10 to the minus 19 coulombs charge, positive or negative depending on the side on that. And the London force, this is the weakest one, so this is going to be the weakest partial charge as well. So generally speaking, the bigger the size of the atom, molecule, electron cloud, the greater the forces, the greater the London dispersion forces will be. So if you look here, we have helium, which is a very tiny atom, smallest atom as a matter of fact, and then going up to xenon, that the bigger the atom, the higher the dispersion forces there. And actually helium has very, very weak forces. It's debatable if helium actually has a liquid or a solid phase. So this is something that we get our government grants to do, and then go to a conference and talk about this stuff. So helium, the atomic distance in solid helium is about 5 angstroms, or what we consider solid. And some people argue, well, that's not really a solid. So it's hard to say if helium has a solid. So that's the forefront of knowledge there. And okay, so the bigger the size, also bigger the size, the higher the force. And also, the closer to a sphere, the lower the forces. So it's harder to polarize something when it's closer to a sphere. So to give you an example of that, imagine you have a carpet that's made of Velcro, and then you have a basketball that's got the other type of Velcro, and it's sticky. Throw a basketball onto the carpet, it'll stick. But what happens if you throw a frisbee on there? The frisbee is going to stick much more. Why? Because it's flatter. So the flat surface, there's lots of interaction here between a flat surface, where two spheres, there's less interaction. So the flatter the molecule and or less spherical the molecule, the stronger the forces. And you can see here with neopentane and normal pentane, or N-pentane. Normal pentane is a flat, straight molecule. Neopentane is a pretty spherical molecule. It's kind of tetrahedral, but it's got the methyl groups, makes it pretty spherical-like. And the boiling point of neopentane is 9.5 degrees Celsius, and normal pentane's boiling point is 36.1 degrees Celsius. So the higher the boiling point, the stickier, the more attractiveness there is between the molecules and the whatever it is you're looking at. So normal pentane, with even though it's the same number of atoms and same type, its flat shape makes it have more dispersion forces. So how can we get stronger? Well, then instead of induced dipoles, we just have plain old dipoles. So dipole-dipole or permanent dipole, these are polar molecules, and the polar molecules have a slightly stronger partial charge, and as such they will have more attractiveness. For instance, the partial positive, partial negative in the polar bonding, polar molecule hydrogen chloride. And I'm trying to draw this here with this electron cloud. Here I'm drawing with the red. You can see kind of a little bit of electron density on the hydrogen, but that chlorine acts like a electron vacuum cleaner, draws a lot of electron density away from hydrogen, making it a very polar covalent bond in a polar molecule. And to illustrate this, so remember, the greater the size, the higher the dispersion force. So here's formaldehyde and ethane. They're both about 30 grams per mole. So they should have about the same amount of forces. But if you look at the boiling point of formaldehyde, it's negative 20 degrees, and ethane is about negative 90 degrees. So the higher boiling point from formaldehyde is the fact that it's a polar molecule, even though it has about the same mass. So you have to go back and remember all the stuff you took, you studied in your General Chemistry 1 course. Which of these molecules have dipole-dipole forces? We have carbon dioxide. If you draw out the Lewis structure and you look at the molecule, it is linear and nonpolar. Therefore, it is not polar, and it has dispersion forces only. Dichloromethane or methylene chloride here is drawn out. It is a tetrahedral molecule with an asymmetry with the chlorines and hydrogens. Therefore, it is polar and will have dipole-dipole forces. Methane here is also tetrahedral. Everything's the same. Therefore, it is a completely nonpolar molecule. And then because of that, it is nonpolar and will have dispersion forces only. Don't let the chlorines, I know the Lewis structure shows them at 180 degrees from each other. It's not really 180 degrees. Remember, this is a tetrahedron, and those bond angles are about 109.5 degrees, thereabout, because of that. So if you'd like, you can pause the video right now and try and work on this problem. If not, you can listen to my solution. Which of these molecules do not have dipole-dipole forces? Water is a bent molecule. All bents are polar, therefore it's got dipole-dipole forces. It also has hydrogen bonds, which I'll talk about soon. Sulfur dioxide is a bent molecule. All bent molecules are polar, therefore it has dipole-dipole forces. Tetrafluoromethane there has it's tetrahedral and each of the atoms the same, therefore this is a nonpolar molecule. It does not have dipole-dipole forces. And then dichloro-difluoromethane, this is a polar molecule. It's tetrahedral, but it's got a break-in asymmetry, just like the methylene chloride. Therefore, this is a polar molecule. It has dipole-dipole forces. So the only one is C. Carbon tetrafluoride is the only one without dipole-dipole forces. So next topic is hydrogen bonds. A hydrogen bond is when you have a hydrogen atom directly attached to a fluorine, oxygen, or nitrogen atom in a molecule. So here I've drawn methanol, CH3OH, and there's hydrogens attached to the carbons. These do not have hydrogen bonds, but there is a hydrogen directly attached to an oxygen in the OH group, and this does have the ability to give and then receive hydrogen bonds. The negative end of the oxygen can receive a hydrogen bond from the hydrogen on another methane molecule. So why do we care? Well, it's what holds DNA together. So DNA has complementary strands. There's one coding strand, one backup strand, and adenine will always bond with thymine or uracil in RNA, and thymine will only bond with adenine, and guanine will only bond with cytosine, and vice versa. And the reason for that is that the adenine and thymine have two spaces that they can hydrogen bond. And adenine cannot bond with itself, and only with another thymine, with a different thymine atom, or molecule, excuse me. Adenine, and it's because of the arrangement of the atoms. It can only in two spots. Guanine and cytosine bond in 3 spots. And again, guanine will only go with cytosine. A guanine will not bond with a guanine, and likewise a cytosine will not bond with a cytosine, nor will an adenine with a guanine or cytosine, and thymine with a guanine or cytosine. And there's only one combination that would work for that. So it's a natural way to back up some of our genetic information. Well, most of our genetic information is in DNA. So, but so they'll stay together, but it occasionally it's not too hard that you can't never unzip it. So there's an enzyme called helicase that will unzip DNA. And why do you want to unzip DNA? Well, for replication or to form messenger RNA for protein synthesis, for instance. So DNA will stick together. And another thing, if you have long hair, which I don't, if you use your curling iron and or your just the flat hair straightener iron, what you're doing is you're changing the hydrogen bond network in your hair, especially with water. What happens if you curl your hair or you straighten your hair? Then it gets wet. It goes back to its normal state. And this is different than a permanent wave or using hair relaxers like sodium hydroxide lye or ammonium thioglycolate or glycolic acid. So that will change the protein structure. So that's different than just using a curling iron, for instance. So okay, so I told you that hydrogen bonds are special. They're dipole-dipole forces. Here are two polar molecules. We have ethanol and dimethyl ether. They're isomers, the same type of atom, different connectivity. The difference is that the oxygen is attached to a hydrogen, and the ethanol has the OH group, where the ether has the oxygen is attached to each of the two bonds is with a carbon. The boiling point for dimethyl ether is negative 22 degrees, and ethanol's is close to 80 degrees. So whereas that 100 or so degrees difference in boiling points, that higher boiling point in ethanol, it's because of the hydrogen bond. So, and let's look at some more with hydrogen bonds. Which one of these compounds is liquid at room temperature? Which one and why? We have formaldehyde. That's a polar molecule, but the hydrogens are attached to the carbons, not attached to the oxygen. Therefore, no hydrogen bonds. Fluoromethane, we have fluorine, hydrogen, but all the atoms are attached to carbon. Therefore, no hydrogen bonds. And hydrogen peroxide, the hydrogens are directly attached to an oxygen, and because of that, there can have hydrogen bonding, and hydrogen peroxide is a liquid at room temperature. Also, so here's a graph. If you look at the y-axis, is the boiling point, and the x-axis is the molecular weight. And you noticed with the carbon family that, generally speaking, as the molecule gets heavier, the boiling point goes up in a relatively straight line, a little skewed. But then you look at water, so hydrogen sulfide, hydrogen selenide, hydrogen telluride, similar to the carbon family, but water is a clear outlier. So why is water an outlier? Because it can give and receive two hydrogen bonds. So, and that's also different than ammonia. I've drawn ammonia right under there with water. Ammonia is a gas at this temperature. Not the pure ammonia NH3 gas, not the ammonia dissolved in water and the ammonium hydroxide, but ammonia is a gas at this temperature. And so why is that? Why is it different? It's because of the two hydrogen bonds that water can give and receive, whereas ammonia can only give and receive one because of the nitrogen site there. Okay, so, and I keep on going with increasing strength. So we had London forces, which were the weakest. Then we talk about dipole-dipole, then a special type of dipole-dipole hydrogen bonds. What's even stronger? Well, it's ion-dipole forces. So ions, unlike polar molecules, have a full charge. By full charge, like a chloride ion, the charge on a chloride and ion is negative 1.6 times 10 to the minus 19 coulombs. The charge on the positive end of a water molecule is less than 1.6 times 10 to the minus 19 coulombs. So the ion has a full charge, therefore there is stronger attractiveness between a dipole molecule, a polar molecule, and an ion. And you're wondering, well, why does it dissolve in the first place? If you look at this, and not really drawn well in the book, but it forms a octahedral shape, and I've drawn the octahedral on the right there. But the chloride anion has 6 waters around it, and the sodium ion has 6 waters around that. So there's each chlorine sodium pair has 12 molecules around it. So the 12 of those attractiveness put together, some of that is greater than the attractiveness between the two ions there. So that is why sodium chloride salt is able to dissolve in water. And also, if you remember solubility rules, and also the Coulomb's law, that the bigger atoms are going to have a weaker charge, and the smaller charges are going to have weaker attractiveness. So sodium chloride is a +1, -1. If you look at calcium carbonate, that's +2, -2. That's limestone. Limestone does not dissolve in water. It's because of the greater charge. It's the small charge alkalis, and they're also big. The alkali atoms and ions tend to be bigger than the other atoms and ions respectively. So that means weaker forces. So that's why they're so soluble, is because they have relatively weak ionic forces, and then as such it's not too difficult to break them apart. But the ion dipole, compared to the other ones, is the stronger force in the intermolecular forces. So here is the summary of this. So we have the weakest force here, London dispersion forces, and everything participates in this. Dipole-dipole, this is for polar molecules. There's a relatively stronger force there, but then we have hydrogen bonding. It's really a dipole-dipole, but we give its own category, and this is for molecules that have hydrogen directly attached to fluorine, oxygen, or nitrogen. And then the ion dipole, where we have an ion attracted to different molecules. And again, the argument here is because of the size of the charge. The smaller the charge, and also the greater the charge, will make it stronger. So that's it for this section. I will see you for the next section.